Assalamu alaikum students. Let's go to a very important proof in statics, which is oftenly very important to understand the fundamental concepts of vectors, and especially a 3D vector, which is basically represented in space. So we very frequently use this formula, which is called as cos square alpha plus cos square beta plus cos square gamma is equals to 1. Okay, and we are also going to be interested if we have this vector A, how to find the directions of this 3D Cartesian vector. Okay, so let's jump and see how we can be able to do this problem, or this derivation rather. Let's say that we have a Cartesian vector representation. Okay, vector A, this vector A we have could be represented by this following relation: A is equals to AXI plus AYJ plus AZK. Okay, which means this vector A has three components: AXI plus AYJ, this is AXI, this is AYJ, and this is AZK. By basically the components actually means that it has three projections. The projection of this resultant vector A on x-axis is AXI, the projection of this vector A on y-axis is AYJ, and the projection of this vector on the z-axis is AZK. Okay, and since this is a vector in Cartesian vector form, we can also represent this vector and take its magnitude, which could be represented as A is equals to under root of ax square plus ay square plus az square. It is represented by equation 2. The resultant vector is represented by Cartesian vector is represented by equation 1. Okay, and since we understood this figure, we know that the direction of Cartesian vector can further be classified as this is our vector A. Okay, the projection of this vector on x-axis is given by this angle alpha. If you look at it, it is given by this angle alpha. The projection of this vector A on the y-axis is given by this angle beta, you can see, and the projection of this vector A is given by on the z-axis. On the z-axis is given by gamma. Okay, so alpha is the angle which the vector A makes with the x-axis, beta is the angle which the vector A, the Cartesian vector A, makes with the y-axis, and gamma is the angle which the resultant vector A makes with the z-axis. Okay, so in order to further simplify it, we can basically be interested what will be the angle of what is alpha, beta and gamma. Okay, to understand this in 3D, we have to look at this figure. Okay, if we just look at the projection of the vector A onto the x-axis, it could be given by this the shaded area. If you look at it, this shaded area, this is the vector A and this is the vector AX. Okay, so we will treat this AX as our base, and from here we basically see, and here to the resultant vector A we can draw this line also. Okay, and basically if you look at it for any triangle, basically you can see at this point, if we are more, if you look this this is our AX. Okay, this is basically base, and again from here to here is basically our perpendicular, and this A is our hypotenuse. Okay, and if you look at it, the angle between the base and the perpendicular, you can see this is 90 degrees. Okay, so this is 90. So again, this is the base, there is an arrowhead over here, and then there is from here we go to, there will be another arrowhead over here. Okay, and if you want, we can also have one arrowhead here also. This is the arrowhead here, and this resultant vector will also have an arrowhead over here. Okay, so all, if you add by head to tail, this the head, and then from here it goes and basically the head of the perpendicular meets with the resultant. Okay, which is our hypotenuse. So if you look at it, So basically we can say our angle which is alpha, this alpha, the cosine of this angle will be adjacent upon adjacent upon hypotenuse, or basically base upon hypotenuse. Okay, so we can say that our base or adjacent is given by ax and our hypotenuse is given by this vector a. Okay, and our hypotenuse is given by this vector a. So this alpha could be represented as cos alpha equals to ax upon a. If you look over here, this is basically again the projection of vector a onto the y-axis. This vector a onto this y-axis is given as again this vector ay, which is the base, and this is our resultant hypotenuse. So we can say again this is our base and this is our hypotenuse. Okay, so and if you look, the angle between the base and the perpendicular is given as 90. Okay, you can see it slightly a different orientation because it is 3D. Okay, it's not exactly what you do it. Base, perpendicular and hypotenuse is simple 2D. This is a 3D, so it's slightly changed angle, but this is 90. And from here also, if you look at it from the side, this angle, you will see that exactly the angle between from the side view, if you look at it, the base and perpendicular are at 90. Okay, and again, if you look at it, the gamma, this is our vector a, and this vector a which makes angle with the z-axis is given as the gamma. So cos of gamma again will be given as this az, which is the base az, and basically this is the perpendicular and this is our hypotenuse. Okay, and again if you want head to tail, this is the head of the base, and then from here we can basically go and add the perpendicular to the head of the perpendicular to the resultant of the vector a. Okay, you can add it over here also. If you are interested, you can still so that it's no confusion. So head to tail, by head to tail here you can add it. Okay, so cos of gamma is given as az upon a. So once this is done, we can say cos alpha is ax upon a, we can say cos beta is ay upon a, and cos gamma equals to az upon a. From here, and we call this as equation 3. So if you go, we can simplify this equation 3 also as cos ax equals to a cos alpha, ay equals to a cos beta, and az equals to a cos gamma. Okay, so this is equation 4. Now if you look at it, we can put the values of ax, ay, az from equation 4 in equation 2. Okay, the value of ax, ay, az from equation 4 in equation 2. But you can see what is our equation 2. This is equation 2. A magnitude of vector a equals to under root of ax square plus ay square plus az square. Okay, so what we do in this equation 2, a equals to, in place of ax we write a cos alpha the whole square plus a cos beta the whole square plus a cos gamma the whole square. Okay, simplify it, the vector a will become as a square cos square alpha plus a square cos square beta plus a square cos square gamma. Okay, so vector a is basically equals to a is equals to under root of a square cos square alpha plus a square cos square beta plus a square cos square gamma. Okay, so we can basically, since a square is in all the three terms it is coming. Okay, so can be a square can be taken out, so we are left with cos square alpha plus cos square beta plus cos square gamma, and let us make this as equation number 5. Okay, now if we say squaring both sides of the equation 5, we will get a square equals to under root of a square cos square alpha plus cos square beta plus cos square gamma, and the whole is basically being squared. Okay, now again we can simplify it. If you look, we can again simplify it, because if the square root sign, if you can say the square root sign could be represented, as the same. Instead of square root we can write it as 1 upon 2, and since we have squared it overall, so it is like this. Okay, a square equals to, and now again if we say this power could be multiplied with, this exponent could be multiplied with 1 by 2. Okay, to, and basically they cancels out and leaving it 1. Okay, so we are looking at the power of 1. So now we can very simply and easily make our equation as a square equals to a square into cos square alpha plus cos square beta plus cos square gamma. and again this a square is basically being multiplied over here. When it goes on the other side of the equal sign, it will be divided. So a square upon a square will be basically, we can put in it as 1. Okay, so we can write it as cos square alpha plus cos square beta plus cos square gamma is equals to 1. So this is the relation that we are looking for. Okay, so again, after proving this relation, we have further said that we know that vector A could be represented as this vector A, which was here. Okay, this vector A, could be represented as vector A. On this, if you look at it, vector A, we have taken a unit vector. On this vector A, we have taken because you can take a unit vector on any vector. And when you take a unit vector on any vector, here you have taken it on vector A, so the unit vector is UA. Okay, so now we can say the vector A could be represented as follows. Vector A equals to magnitude into direction. A vector is defined as it needs to have magnitude and direction. Here our direction is unit vector A. Okay, so once we can write it as this is our vector A divided by its magnitude. Okay, and vector A could be represented as AX upon magnitude of A plus AY upon magnitude of A and AZ upon magnitude of A. Okay, these A's are actually the magnitudes, and this AX, AY, AZ are the vector components of the resultant vector A, are its projections, and this is represented by equation 7. Okay, put the values of equation 3 in equation number 7. Again they are saying the values of equation 3 have to be put in equation number 7. But what is our equation number 3? If you look at it, our equation number 3 is cos alpha equals to x upon a, cos beta equals to ay upon a, and cos gamma equals to az upon a. So over here, ax upon a will put cos alpha, ay upon a will put cos beta j, and az upon a will put cos gamma. Okay, k. So for this, again, unit vector from equation, this was main equation. Okay, so over here unit vector A equals to, over here we'll write cos alpha I, and for ay upon a we'll write cos beta j, and for az upon a we'll write cos gamma. This is equation number 8. So from equation 6 can be written as, equation 6 is what? Vector A equals to magnitude of A into unit vector of A. So we can write it as vector A equals to magnitude a time multiplied by unit vector A, but unit vector A is what? Cos alpha I plus cos beta j cos gamma k. So we can further simplify it. We can write it as vector A could be represented as magnitude of A into cos alpha I plus magnitude of A into cos beta j plus magnitude of A into cos gamma k. So this way basically becomes our equation 9. And very important, if direction cosines are given, 3D vector could be represented by equation number, a 3-dimensional vector, a Cartesian vector could be represented by equation number 9. Okay, so alpha, beta, and gamma are basically the direction cosines of this resultant vector A, which it respectively makes with the x, y, and z axis. Okay, so this is a very simple proof that is very significant when using when you are calculating the projection of vectors in a 3D projection of vectors. So I hope all this information and concept of is quite useful to you, and you have understood the nitty-gritty of these concepts, and thank you very much.